Hello and welcome to the Arcimoto podcast. This week we're going to be talking with Jim Fenton, Arcimoto's senior electrical engineer with a focus on battery systems. Jim's going to be talking about his current work with Arcimoto as well as his 15 years of experience with lithium ion batteries and his 25 years of experience with design and engineering management prior to joining the Arcimoto team. Thanks for tuning in and we hope you enjoy the show.
Hello, thank you for tuning into the Arcimoto podcast. Today we have with us Jim Fenton.
Hello.
You're a battery scientist. How would you explain what you do at Arcimoto?
Well, I wouldn't say I'm a scientist. I'm a design engineer. I was hired with the title of Senior Electrical Engineer Battery Systems.
Oh.
So that's my proper title, but I work on design of battery systems, which includes the electronics and the cells, which when you mix the cells and the electronics, you have a battery.
Beautiful.
So a lot of people confuse the term battery and cells. When you have a single cell, it's not a battery, it's a cell. But a combination of cells is a battery.
Beautiful. And
So
this is what you've been doing for a long time, or?
On and off for a number of years. So I would say this is my third company that I've worked for on electric vehicles. I started on electric vehicles at Ford Motor Company. Way back in 1992, I was hired into the Ford Research Group to work on electric vehicles. At that time, lithium ion cells were in their infancy, so we really didn't work on them. But we did work on advanced lead acid. We worked on nickel metal hydride, nickel cadmium, and hot sodium sulfur, of all things, which normal operating temperature is 300 C to 325 C.
Wow.
And they were fun to work on.
I bet. So you've
Yes.
been a part of the industry as it's moved to where it is today.
Yes. And like I said, at Ford, we didn't work on lithium ion, but I did at A123 Systems when I worked there from 2010 to 2012. And we worked primarily on, I worked primarily on lithium iron phosphate, which is a safer lithium design, less energy dense, but safer, and you can cycle that technology thousands of times compared to maybe 1,000 times for lithium ion cells.
And was that kind of at the early stages of lithium ion in consumer products, or?
At that time, 2010 to 2012, actually, lithium ion and lithium iron phosphate were more advanced, and we at A123 Systems, I was involved in the design and manufacture of the first commercially available lithium-ion starter battery. And the reason that we worked on that was we were helping some European customers because their car sales, or the cost of the price of their cars is based on weight. So if you can move down to the next category lower, even if you make it by 1 ounce, you pay less in taxes. So that's the need to get the weight out of vehicles. And so it's public knowledge now, but we worked on the first commercially available lithium ion battery, starter battery for the sports vehicles at Daimler.
Wow. And so after the seems like multi-decade long kind of run in the battery sphere,
Yes.
what brought you to Arcimoto?
So I designed batteries that would plug into, examples include ultrasound machine, a portable X-ray machine for small children and small animals, and a heart start for portable heart start machines.
Wow.
So that's what I was working on there. But I always wanted to go back and work in electric vehicles.
Nice.
And that's where I cut my teeth, so to speak, when I first started working at Ford in the mid-'90s. And I really enjoyed that, working at Ford for 4 years. And I wanted to get back to it. And my dad, who was He's since passed away, but he was hired by Ford Motor Company in 1965 to work on, of all things, electric vehicles.
Wow.
So he always said there has to be a Fenton always working on electric vehicles. So I am fulfilling my dream and my dad's dream at the same time.
I
So,
like it. And so you've
yeah.
been a part of the Arcimoto team for how many years now?
I just went through 1 year on April 14th.
Congratulations.
Yeah, made it 1 year. So
Nice. Solid. It's
hopefully many more
a
to
massively growing company. A lot of, we've interviewed some people who've been here since the beginning and some
Yes.
people who are relatively new.
come. I am
And
relatively new.
what excites you and keeps you motivated about the Arcimoto vision? Like, exciting without being forward looking of like,
Mhm.
I'm excited kind of for Arcimotos to move in this direction or for Arcimotos to have this impact on cities and the world.
I'm excited to help provide customers with sustainable, safe transportation. I was going to say cheap, but I think that's not the right word. I would say low cost is a better way to put it. Reliable transportation in cities, and I know it's built to go on the freeways, but it lends itself to doing the final mile drive for picking up things, groceries and the like. And I think it's the perfect vehicle for that purpose.
Absolutely.
And I want to work on the battery system design, next generation, to do the three things that are usually required: reduce the cost, reduce the weight, and increase the range.
Yeah,
And that's what we're doing.
I like it.
The standard three.
Yeah,
So
probably a permanent trajectory. As soon as you hit it, you continue to work in that direction.
yes, and that's what I'm enjoying doing, is working on the next generation
Yeah.
design.
To move away from Arcimoto, what excites you about the battery industry as a whole? So you were part of it back before lithium ion or lithium iron was even a thing.
Yes.
And then where we are today, and there's talks of solid state, like not even regarding Arcimoto, in
Yes.
terms of batteries, what excites you?
The whole technology and the number of companies and researchers that are now working to improve the energy density and cycle life. Of course, safety is number one of this technology. So solid state batteries are certainly, I would say, a very good thing to be doing research in and bringing to fruition in the market. The old adage of 10 years from research in the lab to hitting the streets, I think that time frame is being condensed because of the need to get this new technology on the road as fast as possible and move away from fossil fuels as quickly as we can.
Yeah, so you also seems like you kind of align with the Arcimoto mission of clearly there's a climate and clearly we're affecting it in some way,
We are. I was convinced of it a number of years ago, and I'm glad to be part of that paradigm shift to wean ourselves off of fossil fuels and go on renewable energy.
Absolutely.
And even when the cells themselves, the batteries are, they reach their end of life, there's plans to use them, and they can be reused, which is fantastic.
Great news.
Yeah.
What's it like working on a vehicle battery compared to, it sounds like your other companies, maybe not like medical instruments, and like just what interests you about the auto industry and working with them and with batteries?
Sometimes it was a little frustrating working on batteries that were so small because, I don't know, I looked at that and I thought, I'm doing good things for people and helping them with their health, but I've always been interested in batteries that physically move people from one location to another. And because of that, you need bigger batteries. And so I've been, and all of the circuitry and safety requirements that go along with that intrigue me to be able to put together a system so that they all work together. And to do that at the lowest possible cost, still maintain safety, and get the best range as possible based on the technology that you're using. And that's what intrigues me, is the challenge of putting together a whole system that works.
Absolutely. And to kind of break that down, we've talked to so many battery scientists yet, and I haven't heard that you say cells are different from a battery. So could you kind of break that down for a lot of people who may not know of like, why is a cell not kind of a standalone, like a AA battery within the battery pack?
Well, it's a misnomer for somebody to say that a AA is a battery. It's a cell. And a cell is a unique part of a battery. So the cell is a chemical energy source, and that's where it gets its power, its energy. Energy is power over time. So when you buy a new set of cells from the grocery store, you're not buying batteries, you're buying cells, and they will plug into a device to power it based on its chemical composition. A group of cells is a battery, or a cell that has intelligence associated with it, meaning it's being monitored for charge, that's a battery. But a cell by itself with just the positive and negative terminal, that's a cell.
Interesting.
That's it. It's not a battery. It's a cell. So there's a distinction, and I've had to remind a few people whom I work with, there is a distinction. So a cell is a cell.
Yeah, a lot of companies need to rework their marketing if that's the case.
Yes, they do.
Everyone thinks of those as batteries. So could I take a cell out of an electric vehicle and the positive negative would charge a consumer electronic or work for it or power it?
Well, it depends on the application. So normally consumer applications use what are called primary cells. Primary cells are non-rechargeable. So they're designed to last longer because you don't have to worry about recharging them. As a consequence, you will use different chemicals in the construction of the cell to make it last longer. So there's some things in the construction itself and the chemicals and the composition of the positive and negative electrodes, which are connected to the tabs, that are going to be different, knowing full well that you never recharge it. A secondary cell is a rechargeable cell. All automotive batteries and the constituent cells are secondary batteries. They are rechargeable. So they're designed to be recharged. So they may not be as initially as compared to primary cells. Primary cells are usually more energy dense because you can get away with some of the designs because it's never going to be recharged compared to the secondary cells, which are in a lot of cases are not quite as energy dense. So there's a trade-off, and the trade-off is that for secondary cells is that you can recharge them.
When primary cells are made, do they come packaged already charged? Or
Yes.
Is there a way for them to charge it first?
No, they have to come charged because guess what? They're primary cells.
Yeah.
You can't charge them.
But secondary cells come uncharged and we charge them, or they also come charged?
Secondary cells have to be shipped at 30% state of charge or less based on the shipping requirements for lithium-ion chemistries. That's true for lithium iron phosphate and lithium ion cells. So you have to ship them at 30% or less to be within the laws of shipping requirements for those cells. Also, those cells will not be put on a passenger plane ever. They will go on a commercial transport plane or a ship or a train or a truck.
Yeah.
But you'll never see them on a commercial person airline.
It's
because of safety requirements.
Yeah.
You will never see them on there. As far as, you'll see them within people's iPhones and such, but you won't see them as standalone cells being shipped to a manufacturer. That will never happen because of safety.
Yeah, you might be better than a Google search for this. You mentioned cell phones. So is the whole, you don't want it under 20% or over 80% accurate, true, or does it depend on the battery chemistry?
So let me answer that as far as battery life. If you want battery life to be maximum, you don't want to charge it and keep it at 100% charge all the time. Okay, you'll want to charge it up, and you can go to 100%. But what you want it to do is you want it to bleed off quickly from 100%, and you don't want to run it all the way down into the gutter. In other words, you don't want to drain it. So running from 20 to 80% will extend the life of a battery, a lithium ion and lithium iron. So one of the newer ways of charging those cells or those batteries is to do what's called a sawtooth charge, where you charge it up to top of charge, but as soon as it reaches top of charge, you stop the charge immediately. You don't hold it there, and you let it drain off. And you let it drain off based on the load of the electronics that's hooked up to it and the natural relaxation of the cell itself. And then after a period of time, maybe an hour or so, you pop in the charge again and go back up. So the charge waveform looks like a sawtooth. And that's on purpose because you don't want to keep lithium iron and lithium ion at top of charge. You want to bring them to top of charge, but immediately let them go so that you don't, if you keep them and hold them at top of charge, then you're going to not provide their full life.
Prevent them from relaxing, kind of using some terminology you just said.
Yeah.
What does the cell relaxing look like expanding and contracting, or?
No, it's the movement of the lithium ions across the and settling on the electrode after it's been charged up. So there's fast-moving ions and slow-moving ions during the charge, and so there's a relaxation period that you want the lithium ion and lithium iron charged ions to relax and settle down into their relaxation state. And it'll look like an asymptotic curve where it'll drop quickly to begin with and then slow down. So you want to, when you do the sawtooth charge, you want it to relax for a while before you hit it with a charge again. And that way you will extend the life of the cell and the battery.
The question everyone's dying to know is, does a battery weigh more when it's charged?
No.
No.
No different.
Because it's just you're moving electrons from one side to the other?
You're moving electrons from one electrode to the other.
Yeah, and so what is
no difference in weight.
What does the charger for an EV do if it's not, like everyone kind of sees it, especially in animations, as electricity going into the vehicle? So the electricity touches the battery and it like gives it enough energy to move them, or how does that work?
Yeah, so what it does is it pushes the lithium ions across the separator that separates the positive electrode from the negative electrode so that the ions flow through the separator, but the separator itself prevents the positive electrode from touching the negative electrode. If they touched, you would have a short circuit. So separators are very important in the design such that they let the lithium ions flow through when it's being charged or discharged, so that the separator itself has holes big enough for the ions to move through. But the separator won't allow the electrodes themselves to touch each other. And that's separators are a very clever design.
Absolutely. So kind of like at the big scale, cities working with renewable energy to deal with peak demand, they move water up an amount, and then when there's peak demand, they do the water down through it to get hydropower. So it's kind of like that in the cell, though. You put in the energy to move the water up, and in a car battery, you put the energy just switches the sides. That's
correct.
Fascinating.
So the ions are actually moving to the positive electrode when you charge, and the negative electrode when you discharge. So that's a good analogy.
What's your favorite part of an actual FUV, or are you working on the MLM at all? But the favorite part of the batteries that are in our actual machines?
So I'm involved in the next generation FUV design architecture, mainly the architecture, to look at and determine what the trade-offs are going to be for what circuitry we need, what functional things are required based on the requirements, and looking at the lowest cost way. I won't say cheapest. I will say the lowest cost way to properly monitor the state of health of the cells, which is the purpose of the battery system, is to maintain the health of all of the cells. And to do that, you have to make sure that you properly adhere to the voltage limits, current limits, and temperature limits. So as long as you do that and make sure that they are always being meeting the cell requirements as per the cell spec, then you should have a good long life for the cells.
I like it.
A lot of designers don't pay attention to those specs and push them a little bit too hard, and that's why they don't last very long.
To move it away from FUVs, any electric, like let's say a Tesla or any other EV, if one of the cells go bad, can you just replace one cell, or does the whole battery needs to be replaced?
No, it's difficult to replace a single cell. Usually what you would have to end up doing is replacing what's called a battery pack module, which is a group of cells. So it's a subsection of the whole battery pack.
So the whole daisy chain of them.
Yeah, it's a daisy chain. Basically, it would be either a parallel connection or a serial connection, meaning that as you add more battery packs, you're going to increase your voltage. If you add them in parallel, you're increasing your capacity, which is how long the battery can run at a certain current. So when you say capacity of a pack, it's usually measured in amp hours, which means you can provide this current for this amount of time.
Yeah.
So let's see, I'm trying to think of one of the competitors. Well, let's just go with Tesla. They have, I don't know what, it's like 180 kilowatt hour battery pack.
I think 100 in at least the Model X performance, and 120 in some. I haven't.
Yeah, they're low. Some of them are lower, but what that means is that you can provide that much power for that amount of time, but that's the capacity of the battery pack. Its ability to provide the power over a period of time.
Yeah, and so to kind of get a little theoretical with it, using consumer electronics, if we're charging the computer, you can use it while it's charging, or like a laptop. But with EVs, you can't have them plugged in. Like if there's a mobile way, like say you had a big battery bank in the back, you couldn't have it plugged into the vehicle while it's driving. Is that because it'd be trying to move electrons from one side to the other while they're naturally by the engine going to the other side? Or
Well, actually, you can charge a vehicle while it's running. That's called regenerative braking. So when you are driving and you hit the brakes, and the FUV app has this feature, you are, when you're slowing down, and let's say you're not hitting the brake, but you have set the regenerative level that you're comfortable with, you're actually turning around and turning the motors so that they're now charging the battery. So you can charge while you're driving, and that's regenerative braking. And that's how you capture the kinetic energy of the vehicle so that it doesn't go to waste as heat. So a normal internal combustion engine, when you brake, you're wasting all the energy in the disc brakes as heat. You're dumping all that kinetic energy of the vehicle into heat, which is a real waste. The nice thing about electric vehicles is that you can recapture a good share of that, a high percentage of that, and recharge the batteries. And one thing that electric vehicles have as an inherent advantage over internal combustion engines is that electric vehicles are 3 times as efficient in taking the energy that is in the battery as chemically stored energy and providing that as torque to the wheels. Okay, so and the reason I know this is because when I worked at Ford, we measured the efficiency of the electric vehicle that we were working on. In fact, I was involved in writing the first end-of-line test sequence for Ford Motor Company for an electric vehicle. An end-of-line test sequence is making sure that everything is functional. Well, it didn't exist for an electric vehicle. So we took a standard vehicle end-of-line and modified it for our sodium sulfur based electric vehicle, and we changed it. And one of the measurements we did was we did a thumbprint of its efficiency. So we would measure how much energy was coming in, and or let me restate that: how much energy was coming out of the battery and torque to the wheels, because we had it on a dynamometer. And we measured that it was 3 times as efficient. In other words, it was 75% efficient. And taking the chemical energy and applying that as torque to the wheels. An internal combustion engine at that time was 25% efficient. Where's everything going? Heat. It's being lost as heat in the engine and all the mechanical connections and getting torque to the wheel. These days, they're now closer to about 30% efficient. However, the electric vehicles have improved to at least 80% efficient in providing and taking the chemical energy from the battery and applying it as torque to the wheels. So when you compare the two, electric vehicles will always have an inherent advantage of at least 3x over internal combustion engines. And that's just a fact. And that's one of the things that it has going for it. It is inherently more efficient because we haven't figured out a way to get all the energy out of the gasoline. It's lost as heat. So that's a real good advantage for our electric vehicles. They are inherently more efficient.
Fascinating.
Yeah.
And
So it's fun to
absolutely
work. Yeah, it's interesting how much information we gathered when we were making a thumbprint, meaning a snapshot of the state of health of all of the batteries, of the batteries and the cars before we shipped them out. This was when I worked at Ford. And so whenever anything happened in the field, we would look at our thumbprint to look and see, oh, why did that thing fail? Well, all the cells measured good. Not sure what happened. So anyhow, working on the first end-of-line test sequence for Ford Motor Company on an electric vehicle was a lot of fun. And we learned a lot. Here's another unknown fact, at least at that time. If you blow a parallel park in an electric vehicle, at least this was true at that time, you will have wasted 1 kilowatt of energy. And all you're doing is scrubbing the tires. When you do a parallel park, all you're doing is scrubbing the tires. And that's how much energy it takes to do a parallel park. And if you blow it the first time, you've just wasted 1 kilowatt of energy. And that's 1 kilowatt you lost in your range.
Yeah.
It's a lot more efficient to go straight than it is to take a corner.
Interesting.
Because when you're taking a corner, all you're doing is scrubbing the tires. And that takes more energy.
What does scrubbing the tires mean?
Means that you're pulling the tires. When you turn hard and you're doing a backup, you're pulling the tires and you're actually pulling them across the surface of the road. And you're leaving a small amount of tire residue on the road, okay, in order to make that car turn. That's what I mean by scrubbing the tires. You're actually removing some of the tire material off of your tire. If you notice when a big semi is making a turn, watch the back wheels of the semi, and they're being dragged across the road. You're scrubbing the tires.
Wow.
That takes a lot of energy to pull the tires across the pavement. So when you're doing a parallel park, you're doing nothing more than scrubbing the tires, and it takes a lot of energy. And when we measured that, and the fact that you don't want to blow a parallel park, you want to do it right the first time, otherwise you've just taken a kilowatt out of your range. That's wrong thing to do in an electric vehicle. So.
Yeah. Is there a reason that traditional gas vehicles couldn't incorporate that, at least to charge the battery that's for the headlights and all that kind of stuff?
So typically, good question. When I worked at 123, one of our first, when we were working on it, we identified the fact that we could make the starter batteries micro hybrid, meaning that they can take a lot of charge. So lithium ion batteries can take a high amount of charge with no problem at all. Many C, meaning many times the capacity of the battery. And that was one market that A123 went after, and they're still in there big time, in that when you hit the brakes, you can dump that charge, that energy back into the starter battery. And that's what the second generation battery is capable of doing, is receiving that charge. And that's one of the reasons why Daimler wanted it, is because they could store that extra energy and actually reduce the size of their alternator so that they didn't have to have that big of one to provide the low voltage wiring, because they could keep that energy partly in the battery, because every time you hit the brake, it was going to get recharged, to a certain extent. So again, another weight savings. Reduce the size of the alternator, reduce the size of the starter battery. Perhaps you can go to the next level weight class and significantly reduce your taxes. Like I said, in Europe, you pay taxes based on the weight of the vehicle. And anything you can do to get the weight out of the vehicle, like reducing the alternator size and the starter battery size, you're miles ahead.
That's
pun intended.
Yeah. Well, thank you very much. We just about hit our time. I'm curious if there's any kind of, it seems like right near the end, we kind of really got you on the most fascinating topics. And when you come back on, we'll just have to jump right into it.
Well, I'd be happy to come back on because of my many past lives, I do have a lot of experience in different areas and applications for batteries, and I hope to bring that all to Arcimoto's benefit. And that makes me very, very fired up to come into work every day. I enjoy it immensely.
Beautiful.
So,
Thank you, Reverend, for tuning into the show. We appreciate you listening, and we'll see you next week.
thank you.
Bye-bye.